This is regarding this earthing design of building and industrial plants. So I was explaining previously about the classification of the earthing system. You might have commonly come across certain classification like T system, IT system, TNS, TNCS. I will explain about these. Okay, basically what you have to do is just remember these three letters T, N and I. So combine them, you get around 9 combination. In this 9 combination, just you need to consider 3 combination TT, TN and IT. From this TN, you get again 3 more combination TNC, TNS, TNCS. 1, 2, 3, 4, 5. Totally you have 5 system. T basically, see, I means isolated. I means isolated. Load side should always be earthed. You can never have a load side unearthed, no matter what the source is. So, we cannot have I in the source, in the load side. That is the reason I have striked out all those combination where I is located in the load side. Now T and N are allowed in the load side. Now, okay, T means the source side is earthed. N means the load side is earthed. That's why I have removed those combination where N is present in the source side. So this removed, this is removed, 1, 2, 3, this is removed 4, this is removed 5, and okay, N, IN or IT is one and the same. IT system is already there here. That's why I have removed even this. Okay, now let me explain what does TT system means. Okay, I will rub this and then I will only retain, I will explain each individual system separately. Okay, TT system. What is TT system? You have a source, now you have a load. Where does this get connected? Okay. Okay, one and the same. Okay, this is the source, this is the load. A TT system, both source and load are earthed. Okay, this is TT system. Now TN system. A TN system, source is earth, load also is earth. Then what is the difference between TT and TN? I will explain. This TN system has several combinations. This TN system, you have TN, TNC, TNS, TNC, TNS, TNCS. I will explain one by one. Before that, I will go to the IT system. IT system, the source, the load, source side is unearthed, the load side is earthed. This is your IT system. 1, 2, 3, 4, 5. So we have 5 systems. Okay. Now I will explain these two, then I will explain this. If there is a fault, here in the system, what happens when there is a fault in a TT system? What happens? What happens if there is a fault in the system? If there is a fault in the system, the fault current has to flow back. I have made a mistake here. I will correct the mistake. The mistake was not intentional, but when I correct, you will remember something. You know what I have done? At the source side, the neutral was earthed. That is called system earthing. At the load side, I did the same thing. That is not correct. At the load side, you have to earth the body. You have to earth the body. The body is earthed at the neutral side. Okay. So now let's say there is a fault. The fault current flows into the enclosure. Suppose there is a fault here. The fault inside some equipment. The fault current flows into the enclosure, enters the load side earthing, and finally flows through the earth and returns back through the source side earthing into the neutral point. This is TT system. Now coming to IT system, the fault current, there is a fault here between some phase to the enclosure. The fault current flows to the enclosure, then flows into the earthing, flows back, flows through the earth and reaches the source neutral. How? Through the coupling capacitor. This is IT system, the fault current will be very less here. Now in this TN system, I will explain this TN system separately. So I will remove this TT and IT system. And let me go for TN system alone. TNC, TNS, TNCS. I will explain these three. The source, the load, okay. The source is earth, the source neutral is earth. At the load side also the body is earth. But how? Please see this word C. Sorry, see this alphabet C. C means combined. C means combined. S means separate. What is combined? There are two conductors. One is the neutral conductor and the other one is the protective earth. So PE is the protective earth, N is the neutral conductor. When PE and N is combined, when we have a single PEN conductor, it becomes PNC system. When PE is separate and N is separate, it becomes a TNS system. So here the neutral conductor is run like this. A separate neutral conductor will run from the source to the load side. Now, what about the protective earth? We don't have a separate protective earth here because they are combined. So, what do I do? Where do I connect this earthing? Should I earth it separately like this? No. So this becomes a TNC system. This conductor is called PEN conductor. It is both the protective earth as well as neutral. So if there is a fault here, the fault current flows from the enclosure and finally flows back through the PEN conductor. Okay? A part of the fault current may flow through the earth also, a very small portion. Now let me explain about TNS. The source, the load, okay, and the neutral conductor connecting the source neutral to the load neutral, the source, the load, the source side earth, the source side neutral is separate, the load side enclosure is also earth. PE and N are separate. So I run a separate protective earth conductor from the source to the load. This is the difference. PE, sorry, this is PE, this is N. So you can see PE and N are separate. So that becomes TNS system. Suppose there is a fault. The fault current flows through the protective earth back to the neutral. The fault current will not flow through the neutral conductor. It will instead flow through the protective earth conductor. Then, what is TNCS? TNCS is basically, it is TNC and TNS. That is, up to some portion, the system is TNC, later on it is TNS. So if you draw this, the source, the load, the source side earthing, the load side earthing, the neutral conductor. Now, up to this some portion, this is a PEN conductor, that is neutral. The same conductor does the function of neutral and protective earth. After that point, I have a separate protective earth conductor. So this is TNCS. So different places they use different earthing system. This TNS and TNCS are common. But this type of earthing system depends on the local regulations. So you have to check what is specified. See, this system is more applicable for low voltage distribution system. When it comes to your transmission line or 11 kV distribution system, this is not applicable. 11 kV distribution at the sending end, there will be a, let's say, a transformer. For example, you may have a 66 bar 11 kV transformer. So 3 conductors are run. So at the source side, at the load side, we have our switch gear. So a neutral conductor is not required in 11 kV system. We don't run a neutral conductor from the source to load in a neutral system. That is the reason I am telling this is not applicable there. 11 kV system may be like a TT system, but this classification is more applicable to a low voltage distribution. And whenever you are designing a low voltage distribution system and the earthing, please be aware about this classification, and also you should be aware about what is being specified, or what is the requirement as per the local regulator. So without being aware of that, you cannot proceed further. Okay, just one more point before I finally close. Here also your enclosure is earthed. Even the source enclosure is earthed. So please remember that. Okay, so now I will go to the flow chart. See, I have prepared one flow chart in this guideline. So in detail I have explained in another video. You can go through that, and you can go through the guideline also. But I will just tell what is that flow chart all about. The flow chart is nothing but a simple methodology on how to proceed. So the moment you get the earthing design first, you need to get all the inputs. The inputs is the resistivity, the fault current, the local regulations, the plot, etc. Once you have all this input, you start your earthing design. Please check the resistivity, is it high or low? The resistivity is high, please go for some special design. The resistivity is low, please go for normal design. Along with resistivity, you also need to check the plot area. Similarly, the area is very small. Area is small. You need to go for special design. Area is big. You can go for normal design. Now, what is the special design? The special design basically means, see, when the area is small or when the resistivity is high, you cannot go for the normal design because the earth resistance will be very high. In such case, you have to go for some special chemical. You have to add some special chemicals around the earth electrode, that is called treated earth pit. Or you may have to go for some long earth rod which should touch the water table, that is called deep bore earth pit. Or since the area is small, you have to go for a separate area dedicated for earthing, and you have to connect that area to this plat, that is called auxiliary electrode. I will explain about them later. Now, coming to the normal design, what do you do in the normal design? You have the resistivity. First, you have the fault current. Based on the fault current, please first you select the material based on the copper or galvanized iron or aluminum. I don't prefer aluminum because aluminum has problem of unlike iron, it does not corrode itself, but still if you go according to the galvanic the voltage difference between aluminum and iron, there is a problem. So better I don't prefer to use aluminum. So now, okay, I have selected either copper or iron. The next thing is to size. We have to size the conductor. There are certain formulas, you can use them. Once you size the conductor, what do you do next is, based on the area, you determine what is the resistance of the strip or the loop conductors. After determining them, please find out, okay, I have to explain one more thing. See, when we design the earthing system, we have to achieve certain resistance for the earth grid. That resistance, called the grid resistance, is specified by certain owners, but some of them don't specify. But I prefer 1 ohms to 5 ohms. Let's say I want to achieve 1 ohms grid resistance. Now, my present earthing design gives me a resistance of 2 ohms. In order to achieve 1 ohms, I need one more resistor of 2 ohms. 2 ohms in parallel with 2 ohms gives me 1 ohms. So I get 2 ohms from the mesh, I get the other 2 ohms from the vertical driven earth electrodes. So in order to get this 2 ohms from vertical driven earth electrodes, I may, let's say the resistance of each electrode is 55 ohms. I will need around 25 to 30 electrodes. How do I get this resistance 2 ohms of the grid? How do I know the resistance of an electrode as 55 ohms? I will explain in detail. Right now, since I am explaining the flow chart, I am just mentioning about them. So once I get my grid resistance and my layout, and finally then I prepare my material list, that is called bill of quantity. So finally the main output in the earthing design is I have to prepare an earthing layout, I have to make a bill of quantity. The bill of quantity will have the material description and the quantity. So then we complete the earthing design. So I will go more deep into this. The reason I explained about this is I wanted to tell about the flow chart. Okay, now I move to the next topic, material. Material, copper, aluminum or iron. Okay. Now uh, this is a non-conducting metal. That is, let's say, a transformer body. Now this is mounted on a on a foundation, and this is my finished ground level. Now this is my earthing conductor, the main conductor, and this is where I have the earth boss or the connecting location. From here I run a connecting conductor, and here I have the termination, here I have the joint. So now this main conductor can be either iron or copper or aluminum. I will not talk about aluminum anymore, not preferred. When I say copper, it can be insulated copper or it can be bare. Insulated copper will be a cable, stranded cable. A bare copper can be either stranded or it can be solid. Iron can be either mild steel or galvanized iron. This again can be either a rod or a stranded cable or a flat. Mild steel is normally rod. So these main conductors can be many of these. Similarly, the connecting conductors can also be a combination of this. A joint. This joint can be either welding or brazzing or exothermic welding. When I say welding, you have two conductors. I weld it. That is welding. When I say exothermic, this exothermic is normally used for this copper conductors. What they do is, you have two copper conductors. If I want to connect these two, what we do, there is some, you have a box like this. So you run one conductor here, you run one more conductor here. You have a hole here, okay, and inside, they are connecting like this. So they add some explosive powder, and finally they ignite a spark, and then there is some material which melts and it will fuse around this. That is called exothermic welding. There is one more, that is compression joint. Compression joint. What do you mean by compression joint? Your normal nut, bolt, washer, or your connectors. You can have a connector. Suppose you have a conductor like this. There will be a you will have a like this. So there will be some nut bolt. Using that we make the connection. So that is a compression joint. In a project like petrochemical place where sometimes welding may not be allowed, we may go for this compression joint. The material, the joint, depends on again the owner's specification. So please check what is being specified by the owner. Now regarding the termination, this termination can be either welded or compression joint, the only two options. It is better we go for compression joint because of the simple termination with a nut and a bolt and a lug, because welding is better not to do welding at the equipment. So this is about the material. So there is a detailed table in the guideline. Please go through them and then you can select the type of the material. Okay, now let's go to the next important topic, sizing of the conductor.